So we're going to do general relativity part 3. And today we're going to talk about vectors. So if you don't know this already, you should join the Discord. But if you want to follow along, you can go ahead and check the Discord for the notes. And also, I did my YouTube. I have General Relativity Part 1 and 2 up on YouTube. Last week, we talked about the principle of relativity. We talked about time dilation and about Lorentz groups and Lorentz transformations, which were some of the most important things that we talked about with the Lorentz transformations. Like everything we had to do was with Lorentz transformations. And we got a couple different things about going to a new coordinate system and some definitions of some Lorentz transformations. We saw a few of these Lorentz transformations, like rotations in space-time and what was the other one? Oh, a boost, which was basically rotating from space to time and back and forth. And which was some interesting stuff. And now, let's see, where are we at now? So this week we're going to talk about vectors. And the only thing I really wanted to remind everybody about was Minkowski space-time, which Minkowski space is flat space-time. And that's kind of the thing that we know a lot about because it's the most simplest. So like Minkowski space-time would be the one where like there's nothing that's curving space, right? There's no space curvature. It's just there's no energy density.
Explain it with entropy.
But either way, so Minkowski space-time is flat space-time, and but we need more tools to evaluate this. So let's see. So this is flat space-time. But we need more tools to evaluate what flat space-time is. So in comes our vector. So let's talk about. So first we have a 4-vector. A 4-vector is a 4-vector is what we talked about before, where we have our x to the mu, and each of the mu runs from 0, 1, 2, or 3. Now this x to the mu is going to have a kind of a different role in today's lesson, but it's not like going to be different. It's still going to be part of the 4-vector. And there's the thing about the 4-vector that makes it interesting is some of the things that it can't do for the things that we're used to. So like for instance, there's no cross product between 4 vectors. Which is weird, right? Like we're so used to having vectors that have dot products and cross products. And so there's no cross products, and then there's one that's located each of these are located at a point in space-time. At a point in space-time. And I think they're very, very unintuitive, and I think this is where I start to get into a lot of trouble with trying to understand them, right? Like trying to understand what they are, because it's not something that's like straightforward, like even vector spaces I've started to grown to like understand aren't cross products strictly 2-dimensional. Can't you do it, or 3-dimensional? Can't you do a 2-dimensional cross product? They live in a tangent bundle, yes. We're going to talk about the tangent bundle in a second. But they're certainly not intuitive. And one of the things is it does not stretch over coordinates, right? So these are not like something that's going to be like, you know, where we have our 3-vector that looks like this and we have some vector that comes out that stretches over coordinates, right? This is not like that at all. And they cannot be freely moved from point to point. So cannot move from point to point. Freely. And that's kind of like a big thing, right? Because you can't just slide things around. Like they have to go through some sort of transformation if it's going to move in from point to point. And that transformation might change a lot of things. The standard cross product only exists in 3D, while generalizations of it, I believe, 5 and 7 dimensions, maybe other. Oh, I didn't know any of that. Interesting. Okay, so these are some interesting things about 4 vectors that make them act differently than the other vectors that we're used to. Now, there's a real vector space, and I'm not going to write all of these down, but we could write down a couple of things about them. So we can do a collection of vectors that, so a real vector space is a collection of vectors that that added and multiplied by real numbers in a linear way. So like we could have a linear combination of a, a real linear combination of real numbers, a plus b. And Sean Carroll's very, very careful to say real numbers, and I think that's kind of interesting. As opposed to saying scalars, because I don't know. I guess I'm not 100% sure the difference between those, but maybe somebody can clarify a little bit. Or maybe if I just thought about it for a little while, I would be able to put together. But either way, we can do things like distribution properties and whatnot with these real numbers on the vectors that make up the vector space. And then there's the old vector field, which is a set of vectors with exactly one vector at each point in space-time. Okay, so now we have a field of vectors, and we've seen vector fields in some of the things we've done before, where every single point in space-time is in fact a vector. And then we get to the tangent space, and I think this is what Calc Math said, and this is the part that I start to struggle with quite a bit. So as we get to this tangent space thing, we might have to work through this a little bit slowly or work together. So then we get to the tangent space, and this one's usually denoted TP, and we'll call it tangent space. I'm going to write this one out because this one is a bit hard for me to understand. So we'll look at a picture of it too, and it's the set of all vectors. So it's the set of all vectors associated with each point P in space-time. So there we go. Okay, so the set of all vectors associated with each point P in space-time. So let's go look at a picture of that. Hey, boring math professors. Tangent spaces are a little subtle in general. Yeah, it's so weird. Like, okay, let's look at the picture. Need ham. So let's talk about the picture. So the picture has what we'd call a tangent space T sub P, where it's so for right now, just think of I like that line. That line makes a lot of sense. For right now, just think of TP as an abstract vector space for each point in space-time, which that's the thing that is like, yeah, this one's hard for me. But as far as I'm just treating it like a vector space right now, and I think that that's okay. I think that's okay. Anyways, we'll see what happens. A standard vector in space-time is tangent vector to a curve. A parameterized curve, so like that's one thing we could say is like a vector in space-time is a tangent vector to a curve, and the curve would basically be like the manifold. So let's talk about the curve. Okay, cool. All right, so then, so standard vector in space-time, I said this 3 times, is a tangent vector to a curve, a parameterized curve, or a path through space-time. So let's give an example. So now we could talk about the path in space-time. Like each of these coordinates kind of be like subject to a function of lambda, which lambda is some parameter. So the tangent vector, so now our vector is going to be v, and it's going to have some parameter lambda. It's going to have a component that looks like the following. It's going to be like this. So vu is going to be some component of a vector, and that's going to be like taking the derivative of that function with respect to lambda. And that's going to be the vector that makes up, that tangent bundle or whatnot, right? The tangent bundle, are those the right words to say? I think those are the right words to say. So this gives us a full vector. So we can even talk about the full vector. Let's say v is the full vector. And then we can talk about the components and then the directions that they have. So now we have those vectors that consist of in the space-time. And then we can actually give them directions, right, of some unit vector associated with that component, fizzbuzz, element of the tangent. Okay, so the pair of x mu, v mu would be an element of the tangent bundle. Okay, so I guess there's some more work I have to do on understanding those tangent bundles. But So then we can do under a Lorentz transformation. So under a, oh, thank you, by the way, FizzBuzz, for that. Lorentz transformation. I got my goals. Learning GR. Under Lorentz transformation, we would see the following, that like v mu could go to v mu prime, which is equal to, you know, the Lorentz transformation itself times v mu, or v nu. Okay, but the vector v, like proper time, is invariant under the Lorentz transformation. Okay. So if the vector v is invariant under the Lorentz transformation, then we could find the following, that v is equal to v mu times the unit vector associated with that. And then that would equal the vector v nu e to the nu, which is equal to, again, the transformation nu prime mu v mu e to the, wait, what? So this is just nu, which is to say that, so this holds regardless of what v to the mu is. So this is to say that this is equal to e to the, or the vector component of mu is equal to the Lorentz transformation of mu naught mu e of nu. So like you can, basically what I'm saying here is like this is just a transformed vector of the Lorentz. So the unit vector works under a transformation of Lorentz as well, under a Lorentz transformation as well. Which I think is pretty interesting and pretty cool, and it has a nice little unique factor that we'll have to deal with a little bit. But the inverse of the Lorentz transformation, so this is all still part of the same calculation, the inverse of the Lorentz transformation is also a Lorentz transformation, which mathematically looks like the following. So if you take the inverse of a Lorentz transformation, mu prime to nu, that equals the Lorentz transformation of mu to nu prime. So therefore, we can actually, and this is kind of what I said last time when we introduced the Lorentz transformation, is that these transformations themselves, once you do two of them, you have to get back to the original. And another way to say that is that this is equal to the Kronecker delta of what do I have here? I have sigma and nu. There you go. Another one could be, let's see here, nu prime to mu and nu prime rho, and that would be the delta of mu and rho. Okay? Oh, so this leads to the following, which is basically the inverse of that, which is that the unit vector for nu prime is also going to be equal to, some sort of Lorentz transformation on e to the mu, or the basis vector in mu. Okay? So again, just another way that you can say, like, you can transform things back and forth with these transform the unit vectors with the Lorentz transformations, just like you can transform the other vectors. Okay. So now we get to the weird part. We get to even more of a weird part than this, which is dual vector spaces. Okay? The dual vector spaces are really weird. But it starts to get to the contravariant and covariant vectors, which I know is a lot of people like kind of want to know about, because I wanted to know about it as well. Sean Carroll calls that language outdated, which I thought was interesting. But then again, it wasn't Weinberg's book. So let's go over dual vectors. So the space of all linear maps from the original vector space to the real numbers. Okay, so what does that look like? That would be if we take another vector, and we'll unpack what this vector is in a second. This is called a dual vector. Oops, let me make that a big W so it's not confusing. Okay, now This is going to go like the following way. Since these are real numbers, you can pull them outside the vector. So you'll have an a times the dual vector times the normal, or times the vector. Then you'll have a b times the dual vector times the normal vector. And then this is some sort of element of real numbers. But we can also write omega and n are dual vectors, so we can do some. Okay, so these map form a vector space as well. So these form a vector space as well. That's what I'm getting at, these two things right here. So we can also write the following. We can write them some sort of, again, a distributive property plus b. I guess you get more freedom when you aren't stuck with thinking about them as vectors too. I mean, I know they're vectors, but they're a different kind of class of vectors. So there's some sort of distributive property. Like they have properties where you take a vector and you put it by a dual vector and you apply it to a vector. And I suppose that's a different property than you just took two vectors and did something with them, right? Cool. That's an interesting way to think about it. So we can introduce a basis dual vector similar to a basis vector. So Carroll calls it like this, but now we're in the upper index. The same thing, and this can be done by just, I think he said it, we have to demand this of this new basis vector, or basis dual vector, is such that if we multiply the basis dual vector. Now, is multiply the right word too? Or I guess apply. We'll say apply because it's a function. So apply the, and that might have been like a mix-up in my language too. Apply a basis dual vector to a basis vector, then we're going to end up again with the Kronecker delta. So, assuming your underlying fields of the vector space is the real numbers. Sure, yeah, that makes sense. Which it has to be for Minkowski, right? It has to be that for the Minkowski space, I think. I think that's all of the I think that's the understanding of this assumption. Okay. So then we can actually define the dual vectors in the following way that looks very similar to our vectors, where we have the components of the dual vector. I guess I don't think calc math. I think one thing too is that Carroll doesn't nearly talk about it as much of a function as you do, which might just be because he assumes the reader to take that role of it. But you talk about it much more as like a function, like operating on something, than as like as a vector. He just sort of talks about it like a different type of vector. That when you multiply the two together, you get a real, as opposed to something where it's saying about, like you're saying, it's more like an action on a vector. It's weird, like active versus passive verbs between the two. So notationally, and this is just a notation thing for convenience, I guess. Vectors are usually written as v to the mu. And we call them covariant vectors. And these are the elements of the tangent space. So these are elements of the tangent space, P. And then we have another one, and those are contravariant vectors. What did I say? These are contravariant vectors. Hopefully I said that right. Contravariant vectors. And these are elements of the vector space TP. And now we have another one, or the tangent space. And then we have another element, or the covariant vectors, which are the little w to the mu, or sub u, and those are elements of the cotangent space. Okay. But either way, so now we can go ahead and take a look at what it looks like to apply these functions. So if we apply multiply the dual vector to the vector, we're going to get the following. We can write it out in their full forms with as the components and the basis vectors. Also, part of this is just using this enough to be comfortable with the language, which I'm excited about getting there finally, because this is language I've really wanted to learn for a long time. So then this is going to be w mu v to the nu, and then we'll have our two basis vectors. So basically what I'm doing now is taking this basis vector, putting it in, taking this component of this vector and pulling it out. And again, these are like 4 vectors, right? So there's going to be, you can write the 4 vector as a product of the component times the... There's like multiple definitions of vectors in here, of real vectors, not dual vectors. I guess one thing that I'm struggling to understand a little bit is how the dual vector works. This is not right. This is supposed to be new. If you are following along in the note, you have to change that subscript. Second line down, attached to that E. That's supposed to be E sub nu. And it says E sub mu. Okay. So then you can rewrite the multiplication of the vectors. And that's times the delta. This is like super heavy mathematical. Okay, and then lastly, this is going to take, basically the role of the delta function in this is, it is a tensor, but the role of it is to, these indices will contract, and then you'll be left with a w v to the mu. Oh, these are both mu. And that is definitely an element of a real, or of the reals, I should say. All right, so that's just a little calculation, kind of a little acrobatics, what we can do when we actually write out the vectors in their full form and take a look at what they are. So that is to say, oh, did I not keep going with that? Oh, I kind of skipped the next part a little bit. I thought the next part was a little bit redundant. But you can basically do like Lorentz transformations on all of these and look at the product of that, which I think is what it is. I didn't talk about the scalar function, but that would have been probably more relevant to what calculus was saying. In spacetime, the simplest example of a dual vector is a gradient, is the gradient of a scalar function. So that'd be an interesting thing for me to take a look at too. But I figured I'd take a look at that later and kind of understand the meaning of that. But now that I have understood it a little bit more, it might be a little bit easier to do. So then let's just introduce tensors today, and then we'll call it quits. Like I said, today was a little shorter. And then next week we might go back and take a look at that scalar function, or the gradient of a scalar function, and then talk about what you can do with tensors as we get ready to talk about some of the applications in general relativity. So the generalizations of vectors and so tensors are like, you can think of tensors as two different ways that Carroll talks about. Is one is the generalization of these vectors and dual vectors. Like you can write a tensor as either a dual vector or a vector depending on the way that you describe the tensor. So like the rank of the tensor and whatnot. So this is basically to say that it's a multilinear mapping of a collection of dual vectors and vectors to the reals. So, and again, a mapping, so it's like a function, right? So you can take a bunch of these multiplied together, to kind of get to the, so these are a bunch of tangent spaces multiplied together, or cotangent spaces, you're multiplying by the tangent spaces. And this is just a very, very, very general form of what it is. So if there is k of these and l of these, then you say that this is a type KL tensor. And I guess this is also known as the rank, right? The rank of the tensor. So like, for example, you could have a 0, 0 tensor. Let me read the exact thing so I don't screw this up. So a scalar is a 0, 0 type tensor. A vector is a type 1, 0 tensor, and a dual vector is a type 0, 1 tensor. So that was the thing I think that Tesla was sort of like, yeah. So then that's the thing I think that we were talking about with Tesla, that it says that you can take a vector as a type 1, 0 tensor. So you can think of the cotangent version of that as a cotangent space version of that as a dual vector, and it's a type 0, 1 tensor. Okay, where k and l are the type. Okay, so that's cool. So now we can talk about what else I want to do. Oh yeah. So we could do an example of a type of a 1, 1 tensor calculation, which is very straightforward, and this is probably what we're going to end on. So type 1, 1 could look like this, where you'll have the C plus this is just a simplification, I think, or like a something that you could do with this tangents, with this multilinear mapping. CV plus DW is the same thing as saying you can pull out the constants, for the lack of a better word, and then you can write these each as a different type of tensor. I gotta get to the back of this and do some examples, I think. BC, the tensor, was then A to V. And then lastly, plus BD.
Son of Anubis, I got my own special son of Anubis pony now. Thus I rejoice.
So this is something you can do with a vector space. So that's just what you would, that's what you would do. So that's the linear mapping of those two things on each other. Anyways, very interesting stuff, guys. Thank you for sticking around with me. That was interesting. So we have learned that. So next week, I think we're going to get into, hopefully we get into some more juicier stuff. So we'll do some tensor algebra. We'll manipulate the tensors. And then we're going to talk about Maxwell's equations, I think. So we'll get to see some of how these behave.